about the cosmological bootstrap. So take it away.
1 second. Can you see full screen now?
Yep, and we can see the
okay. Okay. Yeah, thanks a lot. Thanks a lot for the invitation to speak. It's really a great pleasure to be speaking at this workshop. Also a great pleasure to see a lot of friends in the audience. I hope everybody's doing well. So yeah, the organizers asked me to speak about the cosmological bootstrap, so that's what I'm going to be doing. So this is work I've been doing in the last couple of years or so, together with these fantastic set of collaborators. But I'd also like to mention that there's a lot of related work now by people, some of you in the audience, that I really enjoyed learning from. And so, you know, bits and pieces I will mention maybe in my talk, but of course I don't have time to get to all of this, but it's a lot of fun actually to be kind of in some small community of people that have been thinking along similar lines. And so I just wanted to mention that. So to begin, let me just remind you that you know, one of the main observables in cosmology are correlation functions. And so we measure correlations at different times in the history of the universe. So at late times, we measure correlations in the distribution of galaxies. Earlier, we measure, you know, correlations in the density, in the temperature of the cosmic microwave background. And then under some relatively mild assumptions, we can in fact trace those correlations back in time all the way to the origin of the hot Big Bang. And so what we usually call the reheating surface. And so that's the earliest imprint that we have of these primordial correlations. And so one of the big challenges, of course, is to try and understand what happened before the hot Big Bang. You know, we actually observationally, we know there had to be some period before the hot Big Bang. We'd like to understand what type of dynamics gave rise to the cosmological correlations. And so now if inflation is correct, and so for the purpose of this talk, this is what I'm going to be assuming, then this reheating surface is actually identified with the future boundary of an approximate de Sitter spacetime. So during inflation, the spacetime is approximately de Sitter. It has a boundary at future infinity, which I'm going to call t equals 0 here. And that future infinity of de Sitter space is attached to the hot Big Bang spacetime. And so we'd like to understand whether we can describe these correlations living at the future boundary of de Sitter, or the initial boundary of the hot Big Bang, intrinsically. Yeah, can we bootstrap these boundary correlations directly without any reference, direct reference to the bulk spacetime and the dynamics during inflation? And the way you get this, of course, is by imposing consistency conditions. You know, and basically the question you'd like to answer is, what is the space of all consistent correlations living on this future boundary that can arise from some consistent dynamics in the bulk spacetime? And so there are in my mind kind of two advantages for this boundary point of view. The first is conceptual, that it focuses only on observables, things that we can actually observe, you know, meaning density fluctuations on this initial slice. And in particular, it does not have to describe, you know, does not make reference to unphysical gauge degrees of freedom, which is what you have to do if you describe local dynamics in the bulk. You have to introduce gravitational fields and coupled fields. And not all of those fields are physically relevant. And a lot of those unphysical fields will actually cancel in your calculations. And at the end of the day, you will describe a set of correlations in physical observables. And so we'd like to turn the question around and describe those physical observables directly. And connected to that is a practical advantage that in many instances, actually, it simplifies our calculations. And these two things are not unrelated. You know, one of the reasons it simplifies things is because it focuses only on physical degrees of freedom. And those simplifications then also will allow us to actually describe things in a kind of a systematic way and map out the space of consistent correlations in a very efficient way, I think. So this bootstrap perspective has been very influential in the field of scattering amplitudes. So there is basically two approaches, you know, the standard or textbook approach of writing down Lagrangian and then perturbatively solving, you know, for scattering processes in terms of Feynman diagrams. And it turns out that if one tries to go just one step beyond textbooks, it quickly becomes very complicated and the calculations become unmanageable. And in some cases, where these complicated calculations have been performed, the answers turned out to be very simple, involving a lot of cancellations between gauge fields and unphysical degrees of freedom. but the final answers were simple. And so this suggested that there should be a simpler way of obtaining these scattering results more directly, by just imposing consistency requirements. So bootstrapping the on-shell amplitudes directly. And so that also has a practical advantage that it simplifies calculations, and it has a conceptual advantage that by simplifying the calculations, it reveals hidden structures. So the answers become simple, and you can actually look for hidden structures, even in theories that you thought you understood very well. So if I have time at the end of the talk, I'm going to mention something called the color kinematics duality for scattering amplitudes, which is a duality that exists just in Young-Mills theory, but it's not so obvious from a Lagrangian perspective that this kind of symmetry exists in Young-Mills. And Young-Mills, of course, is a very old theory, but like we discover new things about these old theories from this new point of view. Okay. And so what I will try to do in this talk is to describe recent progress in trying to develop a very similar bootstrap approach for cosmological correlators. And so the goal will be to try to develop an understanding of cosmological correlators that will parallel the understanding that we have for flat space scattering amplitudes. And you will see that we're really just at the very beginning. We're starting to understand the simplest tree-level processes. In this case of scattering amplitudes, we understand much more. And so we're kind of at very early stages of that program. All right, so the outline of my talk is the following. I'm going to start off describing the basic philosophy or the basic principles of this bootstrap approach. I will then describe how to actually extend it to not just scalar correlators, but correlators involving spinning particles. And then finally, if I have time, I will mention some open problems and maybe some work in progress. We will see how far I will get. All right, so let me start with kind of a basic description of this bootstrap method. And in fact, one thing I would like to highlight is the special role played by singularities, or the fact that we're using singularities as a key input to this bootstrap method. And this is exemplified for the case of the S matrix, where also a lot of the structure of the S matrix is fixed by the allowed physical singularities that these S matrix elements are allowed to have. And here, of course, it's very well known that like when you go on shell, when an intermediate particle goes on shell, so the momentum squared of an intermediate particle approaches the mass of the intermediate particle, then you develop this singular resonance feature. And actually the structure of this resonance, which is kind of this inverse propagator, the structure of this resonance is completely fixed by Lorentz symmetry and locality. Locality means that this pole has to be a simple pole, and then Lorentz symmetry means that it has to be made out of Lorentz invariant momentum in a product. Now then on the singularity, the scattering amplitude must factorize into a product of 3-point amplitudes in the case of a 4-point amplitude. Yeah. And that's a consequence of unitarity. So for a unitary process, there has to be this factorization on the pole. And it actually turns out that for massless particles, having such a consistent factorizations on all scattering channels is very constraining and actually picks out a subset of allowed consistent theories. So for example, if one has a single massless spin 2 degrees of freedom, one can show that the interactions of those massless spin 2 particles have to be those of GR, and massless spin 1 particles, the interactions have to be those of Young-Mills theory. And so as we will see, very similar analyticity constraints will constrain the structure of cosmological correlators. And I'd like to highlight the role of singularities because in our original paper, we kind of used a combination of symmetries and singularities to constrain correlators. And I think that gave a lot of people the impression that symmetries are very important to this bootstrap method. And as you will see from the way of presenting things today, I'd like to de-emphasize the role of symmetries and put more emphasis on the importance of the singularity structures, because it will give us an avenue to kind of actually extend the method towards less symmetric situations. So let me actually describe the possible singularities or the type of singularities that you will encounter for cosmological correlators. So first of all, every single correlator will have a singularity at vanishing total energy. So imagine, for example, this 4-point correlation function here. We usually describe it in momentum space. So then because of the homogeneity of the universe, you know, all the three momenta have to add up to 0. And then the side lengths of this quadrilateral here are the energies of the external particles. And so the claim is that when these energies add up to 0, you develop a singularity. And the fundamental reason for the singularity is that energy is not conserved in cosmology. So it's relatively easy to see from the point of view of the bulk why you get the singularity. So, you know, sorry. Sorry, I was getting a call. From the point of view of the bulk, it's relatively easy to see why you get the singularity is because you're integrating over time. There will always be a factor of e to the I energy of time. And in fact, for a scattering amplitude, you would integrate from -infinity to +infinity, and you would develop a delta function in energy. So that's just energy conservation. In the case of a cosmological correlator, you're not integrating from -infinity to +infinity, but from -infinity to the boundary at t = 0. And so that now instead of a delta function in energy, we'll develop the singularity at e = 0. Okay. And you can also see from this expression here that the singularity will get most of its contributions from very early times when all the fluctuation modes are deep inside of the horizon. And so this is also a kind of flat space limit that you're taking. So then you can show that the coefficient of that singularity is in fact the scattering amplitude itself. Yeah, the scattering amplitude for the corresponding process. So there's an important constraint here that every correlator has a singularity. And the strength of the singularity is determined by the corresponding scattering amplitude. Okay, and this was highlighted or explained in these papers by Maldacena and Pimentel and Raju 10 years ago. So now this is for every correlator. If the correlation function arises from the exchange of a particle, or in cosmology we think of this as the production and decay of a massive particle. You know, because time is running upwards here. In that case, you can have additional singularities, so-called partial energy singularities. And so those singularities arise when the sum of the energies entering a vertex add up to 0. So for example, here, the sum of all the energies entering the left vertex add up to 0. You get a singularity in the left energy. And the strength of the singularity or the residue will be a product of the scattering amplitude on the left, because we're taking a kind of flat space limit of the left vertex. We're taking this vertex and dragging it to -infinity. And a correlation function on the right, okay? So this factorization limit is very analogous to the factorization of the scattering amplitude that I showed at the beginning, but it's a slightly more intricate structure where we're splitting it into a scattering amplitude on the left and a correlator on the right, okay? And then of course, there's an analogous singularity for when the sum of the energies entering the right vertex here add up to 0. Okay, and in fact, these singularities are the signatures of new particles. So these arise because there's new particles being produced in the bulk. And so seeing these singularities in a boundary correlator would be a signature of the presence of these new particles. Okay. And then finally, there in principle can be singularities when for so-called folded or collinear limits. You know, if two of the external momenta align and get folded onto the diagonal, we call this kind of the collinear or folded limit. This limit can be singular if one of the modes has negative frequency. So this cannot happen in the Bunch-Davis vacuum. So for vacuum initial conditions, we expect this limit here to be regular. And so if we imagine that we start from vacuum initial conditions, then in fact, this is an important regularity constraint on the correlator, that we are not allowed to have these singularities. And in fact, recently this was highlighted as a way of testing for the quantum origin of the correlations, because it's a probe of the Bunch-Davis state. Okay. Okay, so these, just to summarize, these were kind of three types of singularities that you can have. So a total energy singularity, two types of partial energy singularities, and then this folded or collinear singularity. And so instead of, and you would encounter these singularities if you just compute correlators in the bulk, okay? And so the philosophy of the Bootstrap will be to turn this around and use these singularity as an input rather than as a calculational output, okay? And see how far you get constraining the full structure of the correlator using these these analyticity constraints. And so it's very simple actually at 3 points, because at 3 points, of course, you have no exchanges. So the only singularities that you can have are these total energy singularities. So you only have point-like interactions in the bulk. And those local interactions in the bulk are in one-to-one correspondence with these total energy singularities. The order of the singularity will correspond to the number of derivatives that the interaction has in the bulk spacetime. And then the structure of the scattering amplitude actually encodes the symmetries of the process, or symmetry breaking, if you would like to study more generic situations. Yeah. So there's a map between Lorentz invariance of the amplitude and de Sitter invariance of the correlator. And by breaking Lorentz invariant of the amplitude, you would also break the de Sitter invariance of the correlator. Okay. And so this was explained very nicely in a beautiful paper by Enrique recently, who showed, in fact, how you can bootstrap this way all the correlation functions of the EFT of inflation, where you have broken boost symmetries. And by parameterizing kind of the amplitudes corresponding to those broken boost interactions, you can generate these corresponding correlators in a very, very efficient way. Now, if you want to go to higher points, then you have to figure out how to connect these 3-point correlations. And so in simple examples, the requirements of these partial energy singularities in the absence of the folded singularities will be strong enough to completely fix the correlator. Okay, but that's only true in very simple cases. And in general, we need to find a way to connect those singular limits. Okay, so we have all these singularities, and we need to know what's the behavior of the correlator away from those singularities. Now, of course, from the point of view of the bulk spacetime, we know what's going on. We know that point-like vertices are connected by the propagation of a particle in spacetime. And so there it's very clear how to make this connection between local interactions. What is less clear from the point of view of the boundary. Okay, and in fact, what is happening here is that a time dependence of this interaction in the bulk corresponds to a momentum dependence on the boundary. So if, for example, this particle here propagates through spacetime and then decays into 2 more particles, this decay can happen at different times. And this time dependence of the decay would manifest itself in terms of a momentum dependence on the boundary of the spacetime. And so we'd like to know what are the consistent time, how does consistent time evolution in the bulk spacetime map onto rescalings of the momentum dependence of the boundary correlators. So if you take this quadrilateral and you deform it, the signal will change. But it can't change in an arbitrary way, but these deformations are constrained. Yeah? And in fact, you can show that in the case of a scalar correlator arising from the exchange of a massive scalar, these correlation functions have to satisfy a differential equation, okay, in terms of the external momenta. Yeah, and so in particular here I've defined a momentum ratio, which is the ratio of the internal momentum ki and the sum of the 2 external momenta k1 and k2. So that gives me a dimensionless momentum ratio. And so there's a second order differential operator in terms of this dimensionless momentum that acts on the 4-point function to produce a source term, which is a contact interaction. Okay. So what this differential operator does effectively is it removes all partial energy singularities from the correlator and produces the corresponding contact interaction that you would get from integrating out the massive particle in the bulk spacetime. Okay. And so then by parameterizing all possible contact interactions, you can determine the corresponding exchange correlators by just solving this differential equation. Okay. So just to give you a little bit of intuition for this differential equation, this is very analogous to what would happen if you multiplied the S channel amplitude by the inverse propagator, S minus m squared. Okay. This would remove the pole of the amplitude, and you would just be left with the numerator, which is a sum of contact interactions, analytic functions of the Mandelstam variables. Okay. So here it's a little bit more complicated because it's a differential equation instead of this algebraic relation. But in spirit, it's the same. Okay. Okay, so this is an important constraint that will connect these singular limits. And so the three requirements, just to summarize, that we have to impose that the correlator has the correct total energy singularity. That means that will allow us to kind of classify the source terms that arise here on the right-hand side. And then imposing that it has the correct partial energy singularities will put boundary conditions that allow us to solve this differential equation here, the homogeneous solutions of this differential equation here on the left-hand side, in combination with requiring that it has no folded singularities. Okay. Okay. So in our paper, we discussed in detail kind of how you can actually solve this differential equation and get kind of explicit solutions for it. They're not very illuminating. But what is illuminating actually is to take a special limit where we take the diagonal momentum of the process and make it soft. Yeah. So imagine you start off with a equal side lengths of this quadrilateral, and then you decrease the diagonal momentum. At first, the signal will change in a smooth way. And so it traces out kind of the EFT expectation of the correlation function. But then as the momentum becomes very soft, the signal starts to oscillate, and it will feel the presence of this massive particle being produced in the bulk spacetime. And in fact, the frequency of these oscillations will depend on the mass of these new particles that are being produced in the bulk spacetime. And I should highlight that this feature here, these oscillations, so they are a signature of new particles, and they're really forced on us by the fact that this correlator has to satisfy consistent factorization. So it's not optional to have this in your solution. It's really forced on you by the boundary conditions of this differential equation. And so recently it was highlighted that this feature, oscillations in the correlation function, is a precise analog of a resonance that we experience for the S matrix. So in that case, we start at low energies where we're just probing the EFT and so contact interactions of the theory. But once we get to sufficiently high center of mass energies in a collider, we start to produce new particles and we see this resonance feature. And so that resonance feature is a precise analog of seeing these oscillations in the cosmological correlator. So now I turned off my phone, so I don't know what time it is. Let me just check. Okay.
Yeah, Daniel, you have about 15 minutes or so.
Okay, that's good. That's good. Okay. So actually, if there's any question, I'm happy to take it now because I'm going to switch gears in a moment. So this would also be a good place to take a question if something was unclear. Is there any question? No. Okay. Yeah. So then I'd like to just describe how the same philosophy applies in the case of not just scalar correlators, but correlators involving massive and massless particles with spin. And kind of our interest in particles with spin is kind of twofold. One is that we know in inflation, we don't just have the massless inflaton, we also have massless gravitons, so spin 2. And so if we'd like to describe gravitons, we need to understand how to include spin into the framework. And second, experience in the case of scattering amplitudes has shown that like the bootstrap is very effective and the constraints are very powerful, especially for massless particles. And there's kind of hidden structures and new relationships that are kind of obscured by Lagrangians, but get highlighted by the bootstrap, especially for gauge theories and for gravity. And so we'd like to kind of see whether those relationships show up in this context as well. Okay, so one way to do this is to start actually with the solutions that we just discussed. So just a solution for scalar correlated scalar fields, and act on them with a set of differential operators called weight shifting operators to produce new solutions that correspond to spinning particles. And this can be spinning particles on the outside, but also spinning particles on the inside. Okay, and actually these weight shifting operators they have a life on their own in kind of the CFT literature, and so they were introduced kind of a while back, and they have a very natural interpretation in this cosmological context as well. So this is in principle a very algorithmic and systematic way of actually not having to resolve the problem every time you study a new process, but actually start with this scalar seed solution that we found once and for all, and then just transform it into new correlation functions involving new particles with spin. Okay. Unfortunately, as the spin of the particle goes up, and especially for gravitons already, it becomes rather complicated and cumbersome to do this. It's probably possible to teach a computer how to do this, but it's not very enlightening, kind of this weight shifting procedure, I think. But what you actually find that for massless particles, the solutions are only rational functions. So the pole structure is actually very simple in the final answers. And so it suggests that you should be able to bootstrap the final answers kind of more efficiently, again, using kind of singularities as an input rather than an output, okay? And so kind of that's the route I'm gonna be following in the remainder. And so it's the same as before. So 3-point functions have only total energy singularities and no other singularities. And you can get them directly by starting with the corresponding amplitude and just dividing by the necessary total energy pole. And you determine the order of the pole just by dimensional analysis. And so it's very simple. You know, it's actually convenient to start in flat space. So what I'm showing you here is 3-point functions involving 1, 2, and 3 particles with spin, arbitrary spin S. This is the scattering amplitude for spin S particle written in spin helicity variables. Okay, and then you just divide by the total energy of the process to get the corresponding flat space correlator. Okay, so it's a very simple algorithm to produce correlators with arbitrary spin from the corresponding spin S amplitudes. And then you can use the fact that the mode functions in the zeta space are very simply related by a differential operator to the mode functions in flat space and transmute these energy functions from flat space to the zeta space. Yeah. So the polarization structure is the same, so that just factors out. And so you have these structure functions, or sorry, form factors of energy that tell you whether you're living in the zeta space or in flat space. And you can get from the flat space correlator to the de Sitter correlator just by these differential operators. Okay. And so again, but it's for arbitrary spin. So you generate the corresponding de Sitter 3-point functions from these answers in flat space. Okay, so that's for 3-point functions. And then 4-point functions, again, we'd like to determine by factorization and maybe the absence of folded singularities. So those are important analyticity constraints. Again, in flat space, because the orders of the poles are all just simple poles, these consistency requirements are very powerful and often fix the answer completely. Yeah? So let me just give you an example. So this is a S-channel Compton scattering correlator of a graviton. So 2 gravitons and 2 scalars on the outside, exchanging a massless scalar. Okay, and the correlation function for that is completely fixed by, you know, having consistent factorization and the absence of folded singularity and consistent total energy pole. It's completely fixed to be this. Okay, it's just simple poles in the total energy, the energy of the left momenta, and the energy of the right momenta. The T channel is very similar. The T channel is just a permutation for this. The U channel is a little bit more complicated because the polarization structure is more complicated, but it also works. It's also completely fixed by these poles. And then just like for the 3-point functions, you can actually transmute the answers to the zeta space. So you can start with these simple seed energy functions in flat space. You act on them with differential operators as a function of the momenta, and you generate the corresponding answers in the zeta space. And you see now the answer in the zeta space has a rather complicated pole structure. So for example, there's a cubic pole in the total energy, and then quadratic poles in left and right energies. Okay, but this complicated pole structure descended or arises, you know, just from this simple differential operation. So there was a very simple pole structure for the seed, and you got more complicated poles from this differential operation. Okay. And in fact, this works in more complicated examples. So you can always write the flat space correlation function as a sum over all helicity contributions of the exchange. And then there will be different polarization structures depending on the polar spins and of the external particles and the spin of the internal particle. And then energy dependent form factors that multiply all these polarizations. Okay, so this is just in very abstract notation, the general structure that these flat space correlation functions have. And then you get to the zeta space by acting with differential operators on these form factors, these energy functions, and you generated more complicated analytic structures by this differential operation. Okay. So it would be very nice to understand these transformation operators a little bit more fundamentally. So the way we were finding them was kind of by cheating and looking at the bulk interactions and the bulk mode functions. And so ultimately we'd like to understand them just intrinsically from the point of view of the structure of the boundary theory. I think that's possible, but we haven't worked that out in detail. And then finally, I should also highlight that actually a large part of the answers in the zeta space, so without taking this route via flat space, is also fixed by unitarity. And so I'd like to just advertise, first of all, the paper by Enrico, Sadra, and Harry that made a very nice point that unitarity in the bulk spacetime corresponds to a cutting rule for the boundary correlators. And so there's a slightly more powerful factorization property of the correlator that holds even away from these singular points. Okay, so this is not a limit that we're taking here. This is actually for all kinematic configurations. This cutting rule here has to be satisfied, and that puts an important constraint on the singularity structure of the final answer. So, for example, if we go back to this answer here, you know, a large number of these poles will actually be fixed by this unitarity requirement. Not all of them. There's certain contact interactions like this one and this one that are unfixed, but a large number of these poles will be fixed by unitarity. And there will be a talk by Scott that just after me that will elaborate on this, I hope. Okay. So now I just have to check how much time I have left.
Yeah, you still have 2 or 3 minutes.
Okay. Okay, so in these remaining 2 minutes, let me first just summarize what I told you. So I have described that singularities control the structure of cosmological correlators. I've also shown you that there are very simple building blocks that are connected by unitarity and local evolution. So 3-point correlators, for example, are very easily generated by these total energy singularities, and then we connect them using both unitarity and local evolution, this differential equation that I showed. And I also showed that very simple seeds can often give rise to more complicated structures through this transmutation procedure that we described. So what we now have is actually a large amount, and I showed really just a very small fraction of that, a large amount of so-called theoretical data. There's many different combinations of correlations that you can calculate in a rather efficient way. And so the question is, are there new hidden structures to be discovered in this data? Can be, actually, if you're interested in this topic, in the case of scattering amplitudes, there's an extremely nice review by Clifford Chung that highlights that, of course, the main purpose of this bootstrap approach was not to just generate, a large class of new scattering amplitudes or correlators, but try to, package the information in such a way that we can gain insights into new structures that are somehow hidden in these answers. Okay. So I just want to give one example in the minute or two that I have remaining, which is this so-called color kinematics duality. So let me just mention, describe for you what this is in the case of scattering amplitudes. So if you look at pure Yang-Mills, and you take the tree-level 4-point function of pure Yang-Mills, it has an S channel, a T channel, a U channel, and a contact term. It's possible to move the information in the contact term into the S, T, and U channels so that the final answer takes this form. Okay, where you have factors that correspond to color information. So there's these structure constants, FABC, appear for each of the different channels. And then there's kinematic factors that depend on the the polarization vectors and so on. And so of course the color factors have to satisfy the Jacobi identity. But the remarkable fact is that these kinematic factors also satisfy the same identity. Okay, so this is what's meant by color kinematics duality, that the kind of the Lie algebra of the theory is reflected also in the kinematics of the of the amplitudes. And then, so that suggests that you could actually exchange color and kinematics, okay? Meaning that you can take all these color factors and replace them by kinematic factors or vice versa, okay? And in fact, if you do this, if you replace color with kinematics, you get gravity, okay? So you get a new amplitude that takes this form, and it's actually the 4-point function of gravitons, okay? And so this is actually just the tip of an iceberg. There's many of these relationships between of squaring amplitudes of Young-Mills into gravity, and those are different theories and so on. Okay, so the question is, does a similar structure exist in cosmological correlators? And sorry, I have to rush a little bit, but I just wanted to highlight that the answer is maybe. So it has been recently pointed out that actually Young-Mills correlation functions in ADS or in de Sitter or in flat space can also be written in this form. And in fact, we just checked that the Compton correlation function that I showed earlier can also be written in this form. So there is a color kinematics duality at the level of correlation functions, yeah, where these kinematic numerators satisfy the Jacobi identity. What is less clear is whether this next step of writing the gravity correlators as a square, so replacing color with kinematics, whether that's possible. Our guess is that the answer is yes in flat space and no in de Sitter space. Okay, and I'd be happy to elaborate why that is. Okay, but also since we have this transmutation procedure of going from flat space to de Sitter space, it may be possible to actually take the double copy of the flat space correlators and see what it implies for the de Sitter correlators. Okay, so there's still some underlying double copy structure, but it's not as manifest in de Sitter space as it is in flat space. Okay, and so okay, I'll stop here and thank you very much for your attention.
Okay, thanks a lot, Daniel, for a nice and clear talk. So we have some time for questions. So I think the first to raise their hand was Alex Vickman. Do you want to go ahead and ask your question?
Oh, hi. Happy New Year to everyone again. Very interesting talk. So Daniel, I'm a bit confused and I have a very naive question. So when we talk about all these poles, right? Then let's say in S or T channel or in any other channel, then it seems that we go to very low transfer momenta to very actually large IR scales. And you also mentioned that this pole and energy should be related to the very early times. But honestly speaking, we have no idea what early times are, right? So for example, our stringy colleagues would like to have inflation for very short actually time, for very limited number of E-folds. And we know from all the scalar fields that this inflation should start at some moment. And that means that we have no idea, no control what vacuum on very large scales is.
Yes,
so
very good.
Am I confused or
no,
it's an assumption?
Yeah, it's a very good question. So actually, I should highlight one thing because I think I forgot to say it. So these energy poles cannot be reached for physical configurations because some of the energies have to be negative. So you can only get there by analytic continuation. So it's not something actually you can measure. Okay.
Yeah.
So the sum of the energies adds up to zero. So some of the energies have to be negative. Yeah. So it's actually not that we're taking the energy to be very small necessarily. We're just adding them up to zero, and with some of them being negative. Okay. So that's the first point. The second point is actually that yeah, we think actually that these poles are a feature of field theory. And you're absolutely right that if we go to very high energies, we expect kind of quantum gravity degrees of freedom to become important, and amplitudes should soften exponentially. And so in a true quantum gravity theory, we do not expect to have these poles. But in an EF, from the low energy point of view, you would see these poles, and you would start with some low energy effective interaction that has this. When you calculate the correlator of that effective interaction, you would get this pole. But then ultimately, this is UV completion and completed. And if it's UV completed in string theory, you would expect this pole to be absent. So the Veneziano correlator, which would complete these EFT correlators, should not have these poles. Yeah. And it's actually a fascinating question what the full correlator would be in a stringy UV completion or any gravity UV completion that should not have these poles. Okay.
Right.
But it's not but that doesn't mean that these poles are not important. They are important in the low energy EFT. But as we saw, actually they're fundamentally important to the structure of the full answer. Okay.
But still, to which extent do you realize that you know the vacuum on very, very long scales?
But I think it's related. So there's, just like for the Bond-Davis vacuum, you could also ask, we're defining formally the Bond-Davis vacuum as infinite frequency, but actually what we mean is that the adiabatic vacuum below a cutoff scale. And so here it's similar, I think, that there's an EFT with a cutoff. If you calculate in that EFT, you have these poles, but of course the poles are kind of a feature beyond the regime of validity of the EFT. Okay, but and then when it's UV completed, then you should see what happens to those poles.
Okay, thanks.
Okay, thanks, guys. So I think Enrico was next.
Hi, Daniel. Thank you very much for the nice talk. I really like. I think it's just a really clear and lucid description of what the ingredients are. I think it's really nice to see it all together. I had a question which is a little bit technical, so hopefully not too technical for everyone. But it was when you use this transmutation operators to act on the flat space correlation functions to get the de Sitter correlation function. What I'm worried is that when you write the flat space correlation function just as amplitude over E, let's say even just contact, just for simplicity, that you are missing the fact that you're missing some finite terms in E, because the amplitude that you write is an amplitude that conserves energy, while the correlator, of course, doesn't. So the correlator will have other terms that are proportional to E that are missed in this formula.
So one thing that's nice actually about the flat space answers is that the poles are all simple poles, independent of the spin. What actually happens in the Sitter space is that the number, because you have to couple through multiple derivatives, the order of the pole goes up with spin. And so you see this from these transmutation operators, that there's S minus one of them when you're acting on the flat space answer. So you're generating higher and higher order poles and more complicated numerators and so on. But actually the flat space answer just has a simple pole. So the only thing that you could be missing is a finite term, like if the numerator is, so we should check out examples. I'm not.
I think in general, those are there for generic, even for scalars, spinning particles. I think they would be there just because you're not conserving energy. So.
This is becoming a bit technical because actually, strictly speaking, actually these spinner brackets have written slightly schematic. You have to be careful actually what you mean by a 3-dimensional spinner and a 4-dimensional flat space. And so I should show you in detail, and that has some slight energy dependence that you can figure out, and it's hidden inside of here. But otherwise, this answer we actually know. We actually computed it from what identities, so we actually know what these answers are, and we know that these are the correct things once you interpret these spinners appropriately.
Okay, so that bracket is carrying those additional powers of E that are invisible.
I think so.
Okay, thanks.
Okay, thanks, Enrico. So Tony had a question in the chat, but maybe it's been answered by Enrico. Tony, do you want to shout up, or has it been answered?
No, I think it's all good.
Okay. Then next was Eugene.
So hi, so very nice. So so to balance out Enrico's super technical question, I'm going to ask a question from somebody who doesn't move on this field. So my super naive thinking about writing Feynman diagrams and doing quantum field theory is basically a very, very clever and way of solving differential equations and Green's functions, right? Doing perturbation theory of Green's functions. So somehow you're saying that, okay, well, we don't actually have to solve the whole perturbation theory. We can just look at the final correlations of this, whatever we are solving, and to gain some insight into the structure of the equation we are solving. Can we export this to other things other than just solving quantum field theory problems, like saying solving Boltzmann equation, for example? It is a differential equation. We can write it down as a field theory, like, we have temperatures and densities, and is there and then when you want to do perturbation theory on Boltzmann equation, you're basically solving a set of convoluted Boltzmann Green's function. And also, like in large scale structure, for example, they are very field theory, like in the sense that you can write down Feynman diagrams. Is there a way to is there something in quantum field theory that allows you to do this, or this is more general? Is a statement about solving PDEs with Green's function in general?
Yeah, the specific example of the Boltzmann equation is throwing me off. Otherwise, I would have said yes. I mean, because so Green's functions are describing causal evolution, and then and they're reflected in the analytic structure of the final answers. So when you're turning things around and trying to ask what are consistent final answers, answers in what outcomes can you get from causal evolution, then it's usually a restriction on the possible analytic structures of the and so any Green's function problem in principle can be maybe inverted, but it depends on the case, I guess, how powerful this will be and what type of constraints you would be imposing. This is, I think, what we're trying to do here is we're trying to understand the rules. Like, we understand from the point of view of the bulk, how the elements fit together, and we're now trying to understand what that translates into on the boundary. And we're so far still doing this in perturbation theory, and actually we're kind of still doing it Feynman diagram by Feynman diagram. And so both of these things are slightly unsatisfying, because in this case of amplitudes, you actually have you understand the rules much more fundamental, in a non-perturbative way. You understand what unitarity and locality and Lorentz symmetry, what those mean, kind of even beyond perturbation theory, which I think we don't quite. And actually, the way the bootstrap for amplitudes works is not just channel by channel, but often it's the final answer summing over all Feynman diagrams. And so that's what makes things dramatically simpler. So there are these, of course, you probably heard these examples where, like, for gravity, the 4-point function has like thousands of diagrams, and the final answer is just like 1 over STU. And so it's those kind of things that you'd like to find. Or anyway, this wasn't a good answer to your question. I think it's a good question whether this can be transported to other fields. And I think, whenever you have a small set of physical input, like, locality, causality, and so on, you might ask yourself whether you could invert the problem and solve the system on the basis of these principles.
Yeah, it seems like you're all trying to put perturbation theory out of business, right? I mean, you're all trying to let's not do perturbation theory, because if you don't want to do Feynman diagram by order, then in a sense you are trying to shortcut your results. So,
if I may mention one concrete example of how you find an obstacle, try to do this for large-scale structure perturbation theory. The same thing you can formulate in terms of Green's function. I think the problem is that you don't understand the analytical structure of those Green's functions, because the metal power spectrum is some messy numerical curve that is not 1 plus k eta e to the I k eta, which is the most beautiful function you could work with. And when you have that, you don't really know how to talk about singularities. You don't get rational functions, and a lot of the scheme is subtracted.
Okay. No, thank you. That's very interesting. Thank you.
Okay, so we are a little bit over time, but I saw that Lam and Tanguy both had their hands up, so maybe you could both ask super quick questions. So Lam, do you want to go ahead?
Yeah, I think I have a quick question for Daniel. Daniel, I have a question about the transmutation operators that you show. They look like they take a fairly simple form, and I wonder if you can motivate the form.
Yes, I was trying to motivate it here, but maybe I went too fast. So, for example, if you look at the mode function in the Sitter space, it's almost, and compare it to the mode function in flat space, which is just this plane wave. Yeah, it just has this extra time dependence that you could generate by acting with this differential operator on the flat space mode function. Yeah, and so if you then want to change these mode functions that you have here from flat space to the Sitter space, you just have to act on act on the answer with 3 factors of this differential operator. Yeah, there's a more complicated one down here that might confuse you, and that comes from the fact that if the vertex has additional time dependence, then this additional time dependence is generated by an energy integral, for example. Yeah, but so there's a whole space of these transmutation operators that you can understand from the point of view of just looking at the bulk time dependence and the bulk mode functions in comparing the Sitter space to flat space. Yeah.
All right. Thank you.
Yeah.
Okay, Tanguy, the last question.
Yeah, this is great, because my question is also about transmutation operators. I had 2 questions, but I'll just ask the first one. It's a practical one. You said it works for, you can use it for all spins. Can you use it also for all masses? Because it looks like the formula you've written was inspired by a massless scalar field.
Yes.
Do you
Yes,
do you use your weight shifting operator to go up in the masses and then transmute, or can you transmute for any mass?
No, actually, yeah, that's a good point. So I think it works for discrete masses because the weight shifting operators actually, you can change masses using weight shifting operators, but only in discrete units. So you can go from massless to from conformally coupled to massless and then, yeah. But so in discrete units of the Hubble scale, you can change masses, but you can't change this continuously. So that's why actually for generic massive particles, I think you always have to solve these differential equations. But once it's one of those members of the discrete series, I think you don't have to solve differential equations because the answers will just be rational functions. And just using the analytic structure will be enough to fix the answers. So there's kind of two different classes of things. If it's generic masses, then it's always differential equations that you are solving. And if it's special cases like conformally coupled or massless, then the answer is so simple that actually you can just solve.
Okay, I see. And the transmutation operators is only for the massless particles.
Yes.
Okay.
Yes.
Okay, great. Thanks.
Okay, guys. So thanks everybody, and special thanks to Daniel for a nice talk. So now we're going to move to the second speaker of the day, which is Scott Melville. So yeah, if Daniel stops sharing, then Scott, you should be able to share. Okay.
Can you see?
Great, we can see it. Can you just move your cursor so we can see it? Yeah, perfect. Okay, so the second speaker of the day is Scott Melville from DAMT, who's going to tell us about constraining the time evolution of cosmological correlators. So thanks, Scott.